All right, so again, we begin on page 24, and normally we look at the calendar first, but I'd like to do one calculus problem before we look at the calendar. So we'll start with number 1 on page 24. Can we go with Tiffany? Okay, so the goal of this section is to maximize or minimize. And if you see a problem that says find the biggest something or the smallest something or the best or the least or the highest, lowest, it's a calculus problem. And these kinds of problems, these optimization problems, are notoriously difficult. So there's a little process that I've written. It's pretty general. We'll come back to the process as we just actually work through a specific problem. So we'll start with number 3. Todd, are you on number 3? Mm-hmm. Okay, thank you. All right, so basic idea here is to draw a picture if you've got a setup which is very visual like this one. So I've got a piece of paper, and on the inside part of the paper is the printed material. So all the type is going to go onto here, and it says that we need 36 square inches. What math word describes square inches? Area. So I know that the area of the printed part of the paper is 36. But then we've got some borders where we're not allowed to put any type, any print, and it says it's 1 inch on the sides and 1.5 inches on the top. So I'm going to draw it up here and around. And it's a little bit narrower on the sides than it is on the top and the bottom. And so we'll just make a note that this piece right here from there to there is how much? That's 1 inch. So 1 inch on each side. And then top and bottom is 1.5. And those margins are non-negotiable. So we have no control over the size of the margins. They're given in the problem. What we do have control over is the length and width of the blue part of this paper. We could try to make the paper really maybe narrow. And so maybe the blue part is really narrow. But what's going to happen if you need to draw a rectangle that's 36 square inches and it's got a really narrow width? It's going to have a very long length. So maybe that's 36 square inches, but then by the time I draw my paper around, all right, now I've got a lot of paper that I'm using if I try to do something like that, right? Okay, well maybe the best rectangle might be what kind of a special rectangle? Maybe a square, right? So maybe you decide, oh, okay, maybe the best one to draw here would be like a 6 by 6 square, and then you draw it around the sides, and maybe that uses the least amount of paper. But the idea here is that there's infinitely many choices that we have, right? You could make the thing really narrow, but then it's very tall, or you could try to make it kind of short, but then it's going to be really wide. Someplace in between is going to be the balancing point, the paper that uses the least amount, I guess the page that uses the least amount of paper. So let's see if we can't find that balancing point using some calculus stuff. So first thing to do is start labeling. And the hint in this problem says label the length and the width of the page that's printed. So I'm going to call L the length of the printed page, and W, actually that's probably a W, right? Doesn't much matter, but we'll call that guy the W, and then the longer one we'll call the L. So length and width. And first thing to do is come up with an equation that relates those things. So we know the area is 36, so what equation can we get? Okay, so L times W is 36. And there's infinitely many solutions to that equation. And of all the solutions to that equation, we want to find the one that minimizes something. we want to minimize the amount of paper that we use. So I'm going to call it P for paper. But what kind of a formula should I be looking for here if I want to minimize the actual amount of paper that I use? Is it a perimeter calculation? It's another area, isn't it? I've just got a bigger area because I have to include my margins. So we know that the area of any rectangle is length times width, but the length is now bigger than it used to be because it's the whole length of the entire paper, including those margins. So what's the entire length of the whole paper? It's L plus 3, right? Because you got a 1.5 at the top and another 1.5 at the bottom. So the length of the entire piece of paper is L plus 3. What's the width of the entire piece of paper? W plus 2. So this guy is the length of entire page. And the other parentheses is the width of the entire page. Okay, is everybody comfortable with that area calculation there? So the question is, of all the L's and W's that multiply to give me 36, because I need that to be true, which one is going to give me the smallest blue calculation? When I can plug in, I'll just do a quick example. What if you plug in, we said we wanted to make it a square. How much is L if it's a square? 6. And how much is W? Also 6. So let's plug in 6 for the L and W into this blue formula. So the first one is a 9. Second one's 8. 9 times 8 is 72. So if you decide you're going to make a square, the printed material, then the entire page has an area of 72. I can't tell if that's good or bad without doing what? Trying another one, right? I have nothing to compare it to. So let's pick another 2 numbers that multiply to 36. Doesn't matter to me. Okay, so what if we make it really long and not very wide? Okay, 12 and 3 gives me a 36. So let's plug in L is 12. So what's the first parentheses? That's 15. W is 3. So the second one is 5. 15 times 5 is 75. Better or worse? A little bit worse. Not that much worse, but worse. Okay, so maybe the square is the best one. But you see, we could play this game with many, many different combinations of L's and W's. And we want to pick the smallest P that we can find. Okay? But can we just keep playing the game? Give me another 2 numbers that multiply to 36. 9 and 4. If we just list all the ones that multiply to 36, couldn't we just grab the smallest one? Why not? Yeah, there's numbers in between. Maybe the right answer is the length is 4.7296 and the width is whatever the width turns out to be for that number. And I'm probably not going to just guess that if I'm doing a trial and error thing. So, so hopefully these calculations here kind of make us understand what the game is, and then we'll use calculus to actually solve it. So first thing we're going to do, let's see, we want to minimize something. If you're at a minimum point, what can you say about that tangent line down there? It has a slope of 0. So it feels like we're going to need to do what to this function? Just take a derivative and make it equal 0, right? Like our favorite thing to do. The difficulty is this function has how many input variables? It has 2. That's multivariate calculus. We are in single variable calculus. So we need to eliminate one of these variables before we take a derivative. And I said there is this kind of general heuristic up here that we'll just take a look at it. Part A, draw a diagram, did that. Part B, find a formula for the quantity to be maximized or minimized. We did that, it's in blue. Part C, use the given information to write the formula found in part B as a function of only one variable. That's where we are right now. We are not allowed to have L's and W's over there. We can only have one letter. Okay, so the way we're going to get rid of one letter is by this black equation. L times W is 36. So it doesn't make any difference to me which one we solve for. So sometimes it's easier to solve for one than the other. Go with that, but in this case, it doesn't matter. So what if we solve for L? What is L equal to from that equation? 36 over W. And so we'll take that 36 over W and just substitute it right in here for this L. So I'll rewrite the blue equation down below. Okay, so this is much better for us because how many variables are on the right-hand side? Just one. And now it's a Calc 1 problem as opposed to a Calc 3 problem. So let's keep on comparing this bolded process here. So what we just did is wrote the formula as a function of only one variable. So we've got that. Part D, find the real-life domain of the formula. Okay, so the domain, that means we're looking for values of W. So let's write it here. What's the smallest W that makes sense? Yeah, I mean, like it could be really close to 0, maybe not ever equal to 0. Could it be less than 1? Yeah, it could be like a half or something. So generally, I'm going to write down, even if it's silly, I'm going to say, well, maybe 0 is the right answer, this extreme. We know it's not, right? It couldn't actually be 0. But certainly, if the answer we get is -5, then that's not right. And then is there a maximum W that we could have? Well, if you keep trying to make W bigger, 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 so I'm stretching this paper widthwise, do I ever run into a problem? Do I? Could I make W equal to 100 inches? Yeah, we have only 36 square inches, but the question is, could I make a 36 square inch rectangle where the width of the rectangle is that long? Oh yeah, so maybe there's a typeface issue here. You get, yeah, but could I make a rectangle that has that as the width and it's still only 36 inches? Yeah, I think I could. I could make a really tiny, tiny length and then go all the way back here and then down. So I could make it really, really short, right? So it feels like we don't really run into a problem, although maybe technically we're going to make our font so small that we can't read it at some point. But it doesn't seem like mathematically anyway, there's an upper limit to this. So that's our domain. And then we come back here. So we just did D, find the domain. And then part E, use the techniques of the previous sections to find the absolute extrema of the function. So we are looking for the absolute minimum value for P. So we'll take this bottom blue equation and do what with it? Take a derivative. So let's take a derivative. What rule do we have to use if the equation is in that form? That's a product. W's times W's. I'm not going to use the product rule. What could I do first? I could distribute. Right? It's not so terrible to distribute this together. So let's go ahead and do that. I got it by being inept at addition. 42. Thank you. Okay, so we FOIL. Any questions about that? All right, now what do we do that it's in this very nice form? Now we'll take a derivative. P prime equals derivative of 42, 0. 72 over W, you could use the quotient rule. You could bring it up as a W to the -1. Some of you, I think, have maybe just memorized a separate rule for 72 over W. What is it? Yeah. So if that looks mysterious, it's just because some folks have memorized a special case. The derivative of a constant over x is just negative the constant over x squared. Plus derivative of 3W, 3. Super. Now that we've got our derivative, set it equal to 0. So let's make this equal 0. And now it's an algebra problem. So spend a minute and see if you can solve for W. Okay, so we solve the algebra somehow. We end up with W is, don't forget the plus or minus, square root of 24, which is about 4.9. The minus doesn't make any sense because it's a width, so we ignore that one. And we get 4.9 only. And what is W equals 4.9 called in calculus speak? It might be the minimum. It'd also be a maximum. but we have a name. It's called the critical point. So W is the critical point or the critical number. So 4.9 is the number of interest. And so the last step in this problem is to really make sure that that's actually the best width, the minimum area of the piece of paper, because flat tangent lines also happen at what other points? The maxes. This could be the absolute worst one that we could do, right? That uses the most amount of paper. So there are different techniques. The one that I'm going to do is going to involve putting, it's the first derivative test that I'm going to do. I'll put 4.9 on my number line. I'm also going to put 0 to cap me because of reality. And then we just have to do a sign test on P prime. So if we pick a number in the first interval between 0 and 4.9, 2. So we're doing negative 72 over 2 squared. That's a pretty big negative number. Add 3. What kind of a thing do we still get? That's a negative there. And if we pick something bigger than 4.9, like 100, negative 72 over W squared is pretty close to 0. Plus 3 is positive. So what kind of a thing is 4.9, max or min? That's a min, right? That's our first derivative test. So I will try to set a good example, and many of you on the last quiz wrote down a phrase that was just about word for word from what I had written here. So since P prime goes from negative to positive at W equals 4.9, we have a min. At W is 4.9. And are you convinced that that's absolutely the lowest point on the graph? Because this is really only a local min. That's what the first derivative test says. But thinking about the fact that 4.9 is the only critical number here, I know that from the beginning of reality, which is at 0 for the width, it decreases, the area of the piece of paper decreases until we get to 4.9 and then increases forever. There's no other number here where it might turn around again and dip below the 4.9 area, right? It's going forever. So it's not just a local, but it's an absolute minimum. And it turns out that's the best width that we can pick. And I've erased it, but we played a game up here where we said, okay, well, what if the paper is square? And I think the area of the paper turned out to be 72, is that right? And then Chris had said, well, what if it's a 12 by 3 rectangle and the area was a little bigger, a little worse at 75? So I'm curious. Let's try plugging 4.9 in. It better be something less than the 72 that we got the first time. So if we plug 4.9 in for the perimeter, I guess I'm also interested in knowing what the length is. So if W is 4.9, and the length, which we know is always 36 over W, can somebody give me an estimate here? 7.3? 2 or 3? 3. So that's our answer. Length is 7.3 inches, width is 4.9. The area of the printed page will be 36. That was required, but it's the total area that I'm interested in. So has anybody done it? What's the total area? How much? 71.07. Better than the 72, which was our initial guess by making a square. Any questions on anything in this problem? All right, so as you practice these problems, just try to keep in mind this very general step-by-step process. It's as specific as I can make it, but it's still pretty general. So that's the basic process to follow when you're solving these problems. Okay, so I said normally we'll look at the calendar first. We'll look at the calendar now. So I just want to highlight a few things. So since test number 2, we have covered a few different topics. Linear approximation and the derivative, that was just our fancy phrase for what? for the tangent line. Okay, so that wasn't too difficult, I don't think. Then we had this next section here about theorems, about differential functions. There was the mean value theorem and the racetrack principle theorem. There were some tricky questions in that section's homework, but to be honest, I don't think either of those theorems is super important for us relative to the next 3 days, the previous 3 days before this one. We had using first and second derivatives. That was about the first derivative test and second derivative test and local extrema. That was tough. Then we had optimization problems. That was finding the absolute max and absolute min, oftentimes on a closed interval. That was tough. And then last class we talked about families of curves, where we found a parabola that had certain characteristics, and then there was this crazy bell-shaped curve that we analyzed, and that was really tough. And so given how tough those 3 days were, and not just tough, but important, I think I'm being very frank when I say I don't think the mean value theorem is all that important for us, but these 3 classes really are. And given that today's class, this optimization and modeling, is also very challenging, I decided that we would kind of spend a day just catching up. There was a day in the calendar, the day before the review day for us, that said to be announced. I put it in there just in case there's a snow day. I'm hoping there's not, because basically we're going to spend today as our snow day. So what we'll do for the rest of the period is, well, whatever you guys want to do. I'm not going to assign homework on this section today, so there's no homework due on Monday. We will continue this section on Monday. There'll be plenty to do in this section on Monday, but I did want to do the one problem. So your task for the rest of today is to do whatever you think you need to catch up on those 3 sections right there. I've put some highlights up here on the board if you need some guidance. In the packet, the homework assignments for those 3 sections, you will find them on these pages. If you just want to know where in the textbook is the homework, okay, for those 3 sections. And if you go to these 3 pages here, 14, 19, and 23, you'll find those graphs that, you know, there was no way to have time to look at in class, but I think there's a whole slew of very good questions related to this particular picture here. So last thing before you guys just go to town, by pushing everything down a day, the dates of all the projects and quizzes and tests are also pushed back a day. So if you've written down any of those dates, they are updated. I printed out a copy of the new part of this schedule. I'm going to hand it to you right now. But I just want to highlight that our 6th project is now getting pushed back. Instead of being due Monday, it's due Wednesday. You have a couple of extra days to do that, and I think it's a challenging project, and it relates to the 3 difficult days that I've been talking about here. So hopefully having a few more days to look at that will help. Our 7th quiz, instead of being Monday, is going to be Wednesday. And then finally, test number 3, I don't know if you'd already written it down, but it was scheduled for December 3rd. So if you have written it down in your calendar, update it. It is now scheduled for December the 5th. Okay? All right, I hope this is a good use of our time. I think it is, so do whatever you need to do.